seminar series. And thanks also to Seiraj, who's made a point of plugging this talk during the 2 seminars I was able to attend. And I'd also like to thank all of you for participating today. And now I have to see how this is going to work. So as Duncan mentioned, I'm a historian of energy, technology, and the environment with a focus on electrification over the course of the 20th century. And I'm often asked why I chose to study the development of the grid. And the honest answer is it's genetic. In this photo, which was taken around 1967, I was probably at an IEEE or Franklin Institute event with a somewhat well-known power systems expert named Nathan Cohn, who was also my father. His passion for his work, just one sec. His passion for his work is what led me much, much later in life to want to study the history of interconnected power systems. I suspect that most of you are engineers or scientists and have a deep and nearly intuitive understanding of power systems and how they work. Today, I'm going to share with you a very brisk story about building the world's largest interconnected machine, hopefully shedding a little bit of light on how and why we got here. This is a particularly American story in that we do not have and never had an electricity czar. Electrification was predominantly, but not exclusively, in the private sector domain here. And in the US and Canada, especially, authority over electrification has been divided between central governments, state and provincial governments, and in some cases, local authorities. In addition, for much of the 20th century, American technologies for interconnection were considered the gold standard. Just as importantly, the development of our grid took place piecemeal over many decades as the result of thousands of separate decisions about how, when, and with whom to interconnect. Through this presentation, I hope to draw some connections between the work Unify is engaged in the coming years and the way in which power system experts addressed operating challenges in the past. When Duncan first contacted me, I noted the key word in your consortium title, interoperability. Interoperability is a relatively recent concept, as some of you may know. The Oxford English Dictionary identifies the first published use in 1965 related to military topics, and the IEEE added the word to its software engineering glossary in 1990 and has maintained the same definition since then. Quote, the ability of 2 or more systems or components to exchange information and to use the information that has been exchanged. Notably, both dictionaries and IEEE list compatibility as a related term, and I certainly hope that applies to this consortium. More significantly, linked power systems have been interoperable from the get-go. By sending information over the power lines in the form of frequency, generators signal to each other whether it's time to speed up or slow down, as do loads that shift on and off the networks. The issue facing power systems experts was how to achieve and improve interoperability as systems became more and more complex. So let me now share an anecdote about when the grid, as we call our multiple North American interconnections, was truly the grid. That is a single interconnected network reaching across most of the United States, much of Canada, and part of Mexico. On February 7th, 1967, the gentleman shown in this photograph, Homer Latzenheier, who was the general manager of the Platte Valley Public Power and Irrigation District, flipped a switch to complete ties between Eastern and Western power systems. In effect, he and his counterparts created the world's largest interconnected machine. For the first time ever, a customer light switch in, say, Seattle was physically connected to a power plant in, say, Philadelphia, Pennsylvania. This was the culmination of 6 decades of effort. Frank Lochicote, with the Bureau of Reclamation, directed the project from Watertown, North Dakota. A journalist there described it this way, quote, all we got on film was intent expressions on the faces of 12 men gazing at a group of electrical meters which recorded nothing at all unusual. And another called the room tension-packed. Here you can see the members of the closure task force directing the project in the upper image. On the left is a frequency chart, which shows at 0 hour, nothing at all unusual. And in the lower right, engineers in Philadelphia intently staring at their meters. Latchicote announced that the closure was complete after, quote, a 19-minute delay during which the two massive power interconnections lazily drifted into synchrony. There are a couple of important points to make about this moment. First, it was greatly anticipated by the experts, but like electricity itself, largely ignored by the public. Second, it worked pretty well, but not well enough. And according to Electrical World, after 2 days of connecting, disconnecting, sending power east and west to east, changing up the schedule, the project proved that the concept of integration across the continent was sound. Latchicote, though, opened the links in July, reclosed them the following December, and participants fully disconnected the system in 1975. So how did we create the world's largest interconnected machine, and why did we abandon it so relatively quickly? Well, let's go back to one of the possible beginnings. Here we see Thomas Edison holding one of his light bulbs, which is interesting, but more importantly, in 1882, Edison introduced a system that linked together generators, power lines, and street lamps into a small network that demonstrated the technical and economic feasibility of electric lighting. It was wildly successful. By 1890, there were 1,000 Edison systems in the United States alone, but it was limited because it used direct current electricity. And at that time, it was excessively expensive and impractical to transmit direct current further than a 1-mile radius from the generator. And the pink square on the right gives you a sense of how much area that covered. In 1893, George Westinghouse demonstrated an alternative approach at the World's Columbian Exposition in Chicago. He used inventions by Nikola Tesla and others to send alternating current over a longer distance and for multiple uses. A larger installation at Niagara Falls confirmed that this was the way to go. It was not long before utilities took advantage of long-distance alternating current and then built links to share power. And companies in California were among the first. So on the left, we see the 80-mile line that linked a hydroelectric plant on the Santa Ana River to Los Angeles. And this was later part of the Southern California Edison system. And on the right, a map of a network linking hydro plants in the Sierra Nevadas to customers in the San Francisco Bay Area. A journalist described a third system, the San Gabriel to Los Angeles line, as, quote, the very quintessence of novelty, originality, and boldness of design. So why did these companies decide to interconnect? I think there are three really important reasons. The first was to achieve conservation as it was understood at the turn of the last century. By linking, say, a hydroelectric plant and a coal-fired plant, the company could maximize the use of falling water and minimize the use of coal, thus saving resources and money. Second was access. The company could access distant energy resources and larger markets through interconnections, and in essence, achieve economies of scale and growth. And thirdly, reliability. A company could obtain system reliability while minimizing its investment in backup generators and batteries. And this is often the most touted reason given today, although not the only one, for interconnections. As mentioned previously, there was no individual or single entity that ran or runs our power networks. Instead, I describe this group of people as a fraternity of experts who collaborated on power systems development. And I need to pause here because I know there are many women in this group today. And you'll note that in this photograph, the vast majority of individuals are men. There are a few women sprinkled among them. And across most of the 20th century, this was an industry both on the academic side and on the government side and in the utility rooms that was predominantly male. And hence I chose the moniker, the fraternity of experts. This image, which is now becoming familiar to some of you, was published in 1904 when power system experts from around the world gathered in St. Louis for the International Electrical Congress as part of the Louisiana Purchase Exposition. And now this is the moment when the older members of this group are allowed to start humming Meet Me in St. Louis, Louis, because that was the very event at which this took place. They came from many countries, multiple types and sizes of power companies, and from universities and manufacturers in order to share their experience in building power systems. And there was a great deal of interest in interconnections. In fact, one of the participants there offered this imaginary projection into the future, saying it would be possible today to operate a string of steam and water power plants in parallel from the Atlantic to the Pacific coast, and to supply power to trunk railroads with so few interruptions that train service could be as punctual as it is today on steam roads. Looking back, the path from Edison's Pearl Street station to a nationwide network seems inevitable. Indeed, in the late 19th century, power system experts were undoubtedly familiar with and sometimes modeled their systems on analogous networks. Think of road networks, railroads, telegraph systems, and especially urban gas lighting systems. And here's a map of a typical railroad interconnected system in the eastern part of the country. But the pattern of early growth suggests that widespread interconnection was not inevitable. In the maps, you see the somewhat modest growth of large transmission lines and networks between 1908 and 1918, while at the same time, as this chart shows, total power generation shot up fivefold. There were multiple factors at play. It was a diverse industry with a variety of interests. There were alternative paths to growth, and there was no overarching game plan. Take the case of industrial manufacturers who strongly preferred to produce their own power. As this graph illustrates, they chose to use in-house generating plants well before 1915 over using central station service. And as a result of some of the energy limitations during World War I, began to switch their preference to central station service after 1915. In addition, it was very difficult to operate interconnected systems. Consider how electricity is different from what's transmitted on other networks: trains, water, gas, even information. Electricity is difficult to store. It has to be available at the instant in order to be useful, and especially in the form of alternating current, exhibits dynamic behavior. I've listed some of the operating challenges here and highlighted frequency control because it was ubiquitous across networks and dogged the industry for decades. So everyone here I know knows that on power networks of any size, the generator, power line, and end-use devices all have to cycle at the same frequency. And while this may be elementary, I still have to offer my analogy. Like a horse pulling a cart, a generator responds to changes in a load. Add more load, generators slow down and frequency drops. Take load away, generators speed up and frequency increases. So every time someone turns a light switch on or off, and again, this is elementary to all of you, the frequency changes. Edison and others after him all included speed governors on their generators to detect changes in speed and restore their systems to the planned frequency. As the use of electricity transitioned from a luxury in the 19th century to a daily necessity in the 20th century, customers came to expect steady and reliable power. Thus, frequency changes affected both system stability and customer satisfaction. In addition to speed governors, operators back then used manual adjustments to keep their systems running smoothly. On linked alternating current system, the problem of frequency control, as you well know, was magnified. As you know, to successfully interconnect, two or more systems had to operate at exactly the same frequency and in phase with each other. A load change anywhere on a linked system affected generators everywhere on the system. The system operators, who at that time were called load dispatchers, had to monitor their systems constantly, maintain contact with their colleagues, and make continuous adjustments to keep their systems in parallel when sharing power. They relied on an increasingly large quantity of data to do this: their own operating experience, for example, projections of demand, and some metered information. In fact, by 1920, the quantity of available data overwhelmed the ability of load dispatchers on larger networks to perform their calculations and put that information to use in a timely manner, which may sound familiar as a big data type of problem. They did, however, have a growing array of technologies to assist with frequency control. Until the late 1910s, the system operators relied on speed governors, early telemeters, hand-drawn curves and data tables, and telephones, as you see in the lower left photograph. Manufacturers offered new apparatus beginning in the late 1910s, of which two became the building blocks of our later frequency and load control systems. The Warren Telechron clock, shown in the middle with its descendant to the right, and the Leeds and Northrop frequency recorder. These two devices worked very differently from each other. The clock was driven by the power system. Thus, an operator could see at a glance if the electric clock was running behind or ahead of a well-calibrated pendulum clock located nearby and could make adjustments accordingly. The second type of device, the recorder, measured and charted system frequency on a roll of paper. An operator could see frequency deviations over time. At the request of utilities, Leeds and Northrop later incorporated a controller that signaled the power system to correct speed automatically. So how did the operators test these novel technologies in these days before modern digital computing? They tested them directly on the power networks. For example, in 1927, the New England Power Company tried both the clock and the frequency recorder on its Harriman station. The result was both did a good job of controlling frequency, and you can see in the chart the difference between manual control and automatic control. But as this quote from the system operator states, if the bulk of the load change should come on one system, then the automatic controllers, while bringing the frequency to normal, would necessarily upset the steady flow of power over the tie line. From this, it appears that it may be necessary to incorporate some sort of tie line load control. Load and frequency, as you know, are inextricably linked. So if the frequency dropped, an automatic controller caused a generator to speed up. Once the frequency was normal, that generator would take up the next increment of load that came onto the system, even if contractually that was not the plan. As power systems experts returned to the drawing board, they began an iterative process that continues today. The next major experiment took place in 1931, when two manufacturers and several power companies tested centralized and distributed frequency controllers and new load controllers on the American Gas and Electric Company network, shown on this map. This network was the nucleus of what became the largest single network in the world by the 1950s, known as the Interconnected Systems Group, or ISG. And I want to note that this process was not without controversy, as the manufacturers of the competing devices accused each other of spreading propaganda and engendering favoritism, while the operators at participating utilities refused to cooperate with each other. It required the owners of the utilities to step in and smooth things over to proceed with the tests. The tests did proceed, and the experts found new weaknesses in their approaches on this larger and slightly more complex system. Experimentation with automatic load and frequency control continued over the next 3 decades. And this chart shows some of the approaches tried during these years. The earliest tests focused on central versus distributed control. By the mid-30s, these experts experimented with tie line bias control. In 1948, utilities tested net interchange tie line bias control, expressed in the equation on the bottom right. And this is likely familiar to many of you because it became the industry standard by the late 1950s. And I will note that this solution favors reliability over other considerations like profitability. Control rooms evolved as well toward the high-tech ones familiar today, and I wanted to share a few photos because I thought you'd enjoy seeing what they looked like in the 1920s, 1930s, and 1950s. Let's take a moment to reflect on this iterative process, which I think is echoed in the concept of circularity that Julia discussed last week. The power system experts identified a problem, devised solutions, tested them, found a functional approach, then were faced with an expanded system reach and complexity, which brought forth new problems, and they started over again. Note also that this process was undertaken by multiple stakeholders, sometimes collaborating and sometimes competing, was almost entirely voluntary, and was tested directly on the operating power systems themselves. Exogenous events and priorities influenced system growth and technical innovation. For example, the massive federal investment in dams that began in the 1930s triggered parallel investment on long-distance transmission and interconnection by both the public and private sectors. Here you can see the rapid rise in installed generating capacity linked to federal dams and a photo of Grand Coulee Dam. It's hard to overstate the importance of World War II in furthering the development of power pools in the United States in the 1940s. We needed lots of power for defense manufacturing, and at the same time, there were restrictions on the use of certain materials and resources for non-defense purposes. As a result, power companies could not build lots of new power plants, and so relied on interconnections to move more power to the war industries and to keep their systems running 24/7. Before the war, it was rare for companies to operate interconnected full-time, and after the war, it was commonplace. The Northwest Power Pool serves as one example of this. Formed in 1942, the pool linked 11 power systems across several states with 13,000 miles of transmission lines and included both the Bonneville and Grand Coulee dams. With no new generating plant installed after that date, but continuous operations, this power pool introduced the equivalent of 100,000 kilowatts in generating facilities at a savings of $25 million. The post-war rebound served as a third type of exogenous influence on system expansion. By the end of World War II, the industry was poised for growth. And this chart compares industrial activity in the dark blue, population growth in orange, and the power generation that took place during those years in teal. You can see that the power use per capita exploded. All three of these exogenous influences, the federal investment, war, and pent-up demand for electricity that followed the war, influenced both the expansion of power pools and development of techniques for operating increasingly complex systems. And here is a list of some of the operating challenges that emerged as power systems grew during the 20th century. I imagine that if I consulted with many people in this seminar, we'd add several more topics to the list, but I'll just let you have a chance to look at them. During those same years, the operators collaborated with manufacturers to develop new tools for system control. And pictured here are just a few examples. On the upper left, the MIT Network Analyzer, which was a physical model of an alternating current power system. On the upper right, this very large economy slide rule, which was used to speed the calculation of generator efficiency to determine the order of dispatch. On the bottom left, the early bird analog computer, which was used to integrate line loss calculations with efficiency calculations. And on the bottom right, an early version of a digital computer to quickly complete calculations and also to model and control system behavior. Without any externally enforced standards, stakeholders also converged on operating solutions that supported the interoperability of their unique and autonomous systems. And here's one very brief example that illustrates how this unfolded in various situations. During the 1950s, there was, quote, a raging controversy that took place amongst power system experts over the proper setting of the bias in the net interchange tie-line bias control equation. Some utilities preferred a lower setting because they benefited economically. Some preferred a higher setting because they could provide and receive more support for system stability. The controversy itself was triggered by repeated disturbances on a system that included the Ohio Valley Electric Corporation, which powered federal uranium facilities. And while I don't have proof, I conjecture that this was partly why it was so urgent to correct the problem. And without discussing in any detail what the issues were, I will just note that it was first vetted by the ISG test committee throughout 1955 and 1956, and then discussed at a major AIEE gathering in 1956. And that was the predecessor to IEEE. The process evolved from vehement disagreement to industry standard as illustrated on this slide. Note the emphasis placed on the autonomous decision-making of system operators that was standard until Congress established a federal responsibility for setting reliability standards fairly recently in 2005. The voluntary standard, first adopted by the ISG Test Committee in 1956, remains the NERC standard today with slightly different representation. So by the late 1950s, an idea first articulated in 1904 began to take shape as a strong likelihood. Both the utility industry and the federal government took steps to prepare for a coast-to-coast grid. Utilities formed the North American Interconnected Systems Planning Committee, known as NAPSIC, and one of the precursors to today's NERC. And this group adopted voluntary standards, like the one described a moment ago, to facilitate successful interconnection across several dissimilar power pools. At the same time, President Kennedy called for a national power survey to provide a roadmap for a single nationwide grid. In 1964, the Federal Power Commission produced the National Power Survey, the first complete one. There was an earlier one attempted in the 1930s that was never fully completed. And this survey predicted a cross-country energy transfer system by 1980, as depicted in this map. And recently, I have noted, when looking at other projections like the NREL SEAM study map, that there are many similarities in terms of how power might move from one part of the country to another. But then we experienced our first major cascading power failure in 1965. And this led many to question the efficacy of interconnections at any scale. This brought the continent's transmission networks to public attention essentially for the first time. Many were surprised to find they were connected to others across several states and even in another country. As a Brooklyn homeowner said, quote, "They, electric companies, shouldn't put all their eggs in one basket that way. Why should we be in the dark because of something that happened in Canada? I've never even been to Canada." Electrical World found that most customers thought the grid referred to a football field. The press, politicians, even some utility executives questioned the wisdom of continuing to build interconnections. But the fraternity of experts had faith in their ability to solve problems, and most in the industry redoubled their commitment to this path of growth. In 1966, NAPSIC, working with the Department of the Interior, formed a task force to plan for an east-west closure. They worked quietly throughout the year, and in November, Secretary Udall announced the planned closure scheduled for the following February. Before the closure, 2 pools in the West closed ties. And importantly, this newly created network experienced significant oscillation problems, which was of concern to the closure task force. In response, NAPSIC also created a blackout planning committee to look at how the West's oscillation would affect a coast-to-coast system. After the closure, only the utilities in Texas were excluded from a grid that served 95% of the continental United States, as well as parts of Canada and Mexico. And as I discussed before, the closure worked at the beginning. There were no major problems reported in the first few weeks. But by summer, oscillations on the West and numerous inadvertent exchanges caused major problems for the utilities. And again, I'm going to ask you to bear with me as I explain the challenge, because I'm sure this is much more intimately familiar to all of you, but I'd like to offer my analogy. Consider 2 spinning balls. If they are to be connected and stay connected, they must spin at the same speed and in the same direction, as does the connector. Otherwise, the system will fall apart. But on the new grid in 1967, not only was the Eastern interconnection 4 times larger than the West, but the links were very small. In addition, the 2 systems tended to be out of phase with each other. On the chart on the right, the shaded area indicates the typical oscillation that took place on the Western system. So interconnected operation of these 2 mismatched systems strained the very small interties, causing local outages and creating headaches for the operators. Task force did work to solve the problems. As this timeline shows, they opened the ties in July. The Western utilities adopted new operating procedures, and the Bureau of Reclamation engineers invented new relays for the ties. They reclosed them in December. During the next 8 months, the relays separated east and west 381 times, but this was the desired result. It protected the two systems from each other. Still, operations were unstable. After 8 years, the utilities ended this grand experiment and permanently opened all 4 ties. The quotes at the top and the bottom illustrate how the power system experts viewed the coast-to-coast grid at the time, and then, as the WAPA executive's quote illustrates, several decades later. The 2 decades after 1975, the companies replaced the 4 alternating current ties with 6 DC ties, allowing the 2 giant eastern and western systems to operate out of synchrony with each other and share modest amounts of power. Referring to my spinning ball analogy, the DC ties worked like swivels on the connectors between the balls. So technically now, while the 4 major North American grids are connected, as this image indicates, they are not interconnected. Much about the industry has changed since 1975 as well. State and federal governments revised regulatory relationships with each other and the industry. Industry participants reorganized under the new regulatory regimes. Newcomers introduced new technologies, and there are new imperatives, challenges, and opportunities for moving power from generators to users. Despite all these changes, or maybe because of them, the grid is still characterized by a gaggle, as one utility executive described it, of government agencies, profit-seeking companies, cooperatives, regulated utilities, and even homeowners that generate and distribute electricity in North America. Looking ahead towards a renewables-rich grid, as we like to say in Texas, this is not our first rodeo. There were many points in our history when experts sought to integrate renewables, mostly hydro, into our networks. There are many parallels in terms of moving electricity from distant energy resources to power customers. But there are also major differences, as types of renewables and scale of systems pose different questions about integration and operation. Finally, during the 20th century, we built large interconnected systems linking large generating plants to power customers with an emphasis on economies of scale and reliability, and, as Seiraj would urge me to include, driven by electromechanical machines. But we have to ask, what will be the 21st century paradigm for electrification? Even larger networks, probably made up of grid-forming inverters perhaps, smaller islanded systems, a return to isolated plants, or perhaps new technologies and techniques we haven't imagined yet. I leave that to you, the new fraternity and sorority of experts, to debate. Thank you.